Why did physicists want to chop a photon into pieces? And what came out of it? Hello, you're watching the channel Bold Science with Firyuza. The end of the 19th century. Physics looks almost complete. Newton's mechanics describe the motion of bodies. Maxwell's equations explain electricity, magnetism, and light. Experiments confirm theory with unsettling precision. It seems the world is understood. Only technical details remain. And it is precisely at this moment that physics runs into a wall. Physicists were studying the radiation of a perfect black body, an idealized object that absorbs and emits electromagnetic energy as efficiently as possible. Let me clarify. A black body is an imaginary ideal object that absorbs all incoming light, reflects nothing, and emits light solely because of its temperature, not because of its shape, color, or material. This means that a black body glows not because it is red, shiny, or made of some particular substance, but only because it is hot. If you take two perfect black bodies at the same temperature, they will emit exactly the same radiation regardless of what they are made of or what shape they have. Color, material, and surface matter for ordinary objects. For a perfect black body, only temperature remains. That is why physicists use it as a benchmark. If we understand how a perfect black body radiates, then we understand thermal radiation in general, whether from a stove, a lamp, a star, or the universe itself. Scientists had already measured what kind of light a heated body emits. This is called the experimental spectrum. Now it had to be explained using equations. For long wavelengths, the theory worked well. For medium wavelengths, it worked too. But for very short wavelengths, in the ultraviolet, something strange happened. If one strictly trusted classical physics, the result was that as the wavelength decreases, the body should emit more and more energy, with no limit. In other words, according to the formulas, the energy of radiation does not just become too large, it becomes infinite. And that cannot happen in reality. Any heated object, from a stove to the human body, would have to emit infinite energy at short wavelengths. The universe shouldn't exist. This is not a philosophical problem. It is a mathematically unavoidable conclusion drawn from a perfectly consistent theory. That is how one of the most disturbing names in the history of science was born, the ultraviolet catastrophe. In 1900s, Max Planck took a step that he himself considered forced. He was looking for a formula that would match observations, and he proposed an assumption. Energy is not emitted continually, but in discrete portions. The smallest portion of energy is proportional to frequency. Thus, a new constant appeared in physics, Planck's constant. Planck's formula matched the experiment perfectly, across all ranges, with no infinities, with no catastrophes. The problem was solved, but at what cost? This is a key point that is often forgotten. Planck didn't consider the quantum to be real. He didn't quantize light itself. He quantized the energy of hypothetical oscillators. For him, the quantum was a mathematical trick, a way to calculate energy correctly, nothing more. He could say that Planck didn't discover the quantum world. He stumbled into it by accident, apologizing at every step. And when he realized what he had done, he was frightened. If energy is emitted in discrete portions, a simple and devastating question arises. What happens in time? A body cannot emit a quantum instantaneously. Emission takes a finite amount of time. Now take a smaller time interval. During that interval, the body emits less than 1 quantum of energy. So what does that mean? Can a quantum be divided? Then it is not minimal. Then it doesn't exist. The logic is flawless. That is exactly why physicists of the early 20th century decided we'll use a formula, but we won't take the idea seriously. After Planck introduced the quantum of radiation, physicists tried to split light experimentally. They weakened the radiation to the extreme and stretched it out in time, expecting to observe energy being transferred in tiny fractions smaller than a quantum. But the experiments revealed something strange. The energy of a quantum doesn't divide. It is transferred either as a whole or not transferred at all. So the attempt to chop light led to an expected conclusion. Light has an indivisible portion. Even Planck himself tried to get rid of quanta. Again and again, he tried to force the genie he had released back into the bottle. But it was already too late. The era of quantum physics had begun. This is an important place to pause. People often say, Planck's constant is very small. That's misleading. A better way to say it is this. Planck's constant sets the scale at which classical physics stops working. Planck's constant is the minimal quantum of action, energy times time, momentum times length. It means you cannot make energy and time arbitrarily small at the same time. You cannot define position and momentum with unlimited precision. This is not a limitation of your instruments. It is a limitation of reality itself. Albert Einstein took the quantum seriously. He said, if energy is emitted in quanta, maybe light itself is a quantum. Not a wave chopped into tiny pieces, but a stream of particles. That sounds like a challenge to common sense. After all, interference, diffraction, polarization, all of these are wave phenomena. And yet Einstein went all the way. The photoelectric effect has a solid experimental basis. Light ejects electrons from a metal. But there are strange facts. The intensity of light doesn't affect the energy of the electrons. Only the frequency does. Classical theory demands that an electron should accumulate energy gradually, but it doesn't. It either flies out immediately or it doesn't fly out at all. Einstein explained this with a single formula. One photon, one electron. Either the energy is sufficient or it isn't. You could put it this way. The photoelectric effect is an experiment that humiliates classical theory. It was precisely for explaining the photoelectric effect that Einstein received the Nobel Prize. Not for relativity, but here's the irony. People didn't believe him. Why did physicists resist? Because it was too radical. First, energy is quantized. Then, light itself is a particle. That undermines the foundations. Even Planck didn't support Einstein and said that with his light quantum hypothesis, Einstein had gone too far. Even Bohr had doubts. For many years, Robert Millikan tested Einstein's formula. He confirmed it with better than 1% accuracy. And then he declared, the formula is correct, but light quanta don't exist. A rare case in the history of science, the experimental loss to his own experiment. In 1922, Arthur Compton performed the decisive experiment. X-rays quanta scattered off electrons as if they were elastic particles. Light bounced off electrons the way soft elastic balls would. Before Compton, light interfered. After Compton, it also bounced. And physics found itself in a new dead end. Experiments showed that light is a wave, and at the same time light is a particle. But how is it possible? If light is a particle, what does it interfere with? And then the real horror begins. Single photons, one at a time, produce an interference pattern. So the question arises. What does one photon interfere with? With itself? With possibility? With a future measurement? There is no answer yet. The quantum of action is not just a number. It is the first crack in the classical picture of the world. The moment physics said, we can no longer talk about what is. We can only talk about what is measured. This is where quantum mechanics begins, and all of its paradoxes. But that's for other videos. Don't forget to subscribe to the channel Bold Science with Firyuza and watch the next episode.